Right, let's dive straight into this explainer. Today, we're basically opening our mental textbooks to page 71 for what I like to call the master review exercise. If you've been following along with our core science concepts, you already know just how incredibly interconnected this universe of ours really is. So today, we're going to unify fundamental physics, geology, and environmental science into one big cohesive journey. We're connecting the tiny micro forces that push an object across your desk all the way up to the massive macro forces that shape our entire global climate. Here's our game plan for today. 1. The ultimate review exercise. 2. Motion, force, and energy. 3. Inside the Earth's layers. 4. Forces shaping our planet. 5. Climate and human impact. And finally 6. The final question. All right, section 1. Motion, force, and energy. To get our gears turning, let's kick things off with a quick pop quiz. Do you know the distinct difference between rotation and revolution? I know it's a super common mix-up, but getting this straight is absolutely key to understanding planetary mechanics. According to our sources, rotation is actually a specific form of rotary motion where a body spins right on its own axis. You know, exactly like the Earth spinning to give us day and night. But that's just one type. We've also got rectilinear motion, which is just movement in a straight line, kind of like a bullet train on a perfectly straight track. Then there's oscillatory motion, which is this vibratory movement that repeats at regular intervals. Think of a pendulum swinging on a grandfather clock. And finally, circular motion, like a Ferris wheel going round and round. But here's the thing, motion doesn't just happen out of nowhere. It needs a push or a pull. It requires force. And to actually measure those physical pushes and pulls causing the motion, we use a spring balance, which you might also know as a Newton meter. Inside, there's a spring attached to a hook, and the mechanics are beautifully simple. The spring physically stretches when a force is applied to that hook. The bigger the force you apply, the longer the spring stretches, and the pointer slides down the scale to give us a larger reading. It's just a direct, visible measurement of physical force in action. Now, obviously, applying any kind of force requires energy. Energy is fundamentally just a property of matter that can be converted from one form to another. Our sources break down the origins of this energy into two main buckets. On one side, we've got renewable energy. This is stuff that can be replaced, things like solar, wind, and geothermal energy, which is drawn from heated groundwater. But on the absolute opposite side, we have non-renewable energy. These are our fossil fuels: coal, oil, natural gas. Once we burn these to release their energy, that's it. They cannot be replaced. And hey, keep this in the back of your mind, because this specific energy conversion is going to be a huge deal when we reach the end of our explainer. Moving right along to section 2, inside the Earth's layers. Before we actually peek inside, let's go ahead and debunk a massive assumption right off the bat. The Earth is not a perfect sphere. Thanks to the literal forces of its own rotation that we were just talking about, it bulges at the equator and kind of flattens out at the poles, which means mathematically our planet is shaped a bit more like a lumpy potato. The actual proper scientific term for this shape is a geoid. So, to really comprehend what makes up this massive geoid, our text uses this fantastic, really simple visual analogy. You can literally think of the Earth like an apple. Just like an apple, the Earth is composed of 3 primary layers. You have a thin outer skin, a thick middle flesh, and a really dense center core. Applying this directly to the scientific model, the apple's skin is the Earth's crust. That's our outermost, thinnest layer. Right below that, the flesh represents the mantle, and that makes up the vast bulk of the Earth's total volume. Finally, deep down in the center, we have the core. And the core is actually split into 2 parts. There's a liquid outer core and a solid inner core, both driven by just immense internal pressure and heat. Now, if we zoom all the way back out to that thin outer skin, the crust, we find a pretty complex recipe. It all starts with basic elements, like oxygen. These elements lock together to form minerals, and then those minerals bind together to create the actual rocks beneath our feet. We're talking igneous rocks, which include volcanic basalt and granite, sedimentary rocks, and metamorphic rocks. All right, section 3, forces shaping our planet. So the first combatant in this geological battle are the internal forces. These act from deep within the Earth, and they're responsible for building the landscape up. We're talking dramatic events like earthquakes and faulting, for sure, but also folding. See, when the Earth's crust is subjected to massive compressive forces, it literally folds under the pressure. An upward convex fold is called an anticline, while a downward fold is known as a syncline. And this is exactly how massive fold mountains are born. The crucial takeaway here is that immense internal pressure builds up over time and is often violently released, and volcanism is the perfect illustration of this. Deep underground, molten rock is called magma, but when those internal forces push that magma all the way up and it actually erupts onto the Earth's surface, that's when it becomes what we call lava. It's a spectacular process that creates towering volcanic mountains and even entirely new landmasses. But here's the catch. While internal forces are busy building the Earth up, our second combatant, external forces, are constantly, relentlessly working to tear it back down. From the outside, the crust is battered by physical and chemical weathering, denudation, which is basically just the stripping away of the Earth's surface, and erosion. The main agents of this erosion are wind and water. In desert areas, for example, wind is a highly significant agent, carving out these distinct landforms like Barchan dunes and loess deposits. It's just this constant, endless cycle of building up and wearing away. Which brings us to Section 4, Climate and Human Impact. Basically, everything we've discussed so far, from the sedimentary rocks to the air we breathe to the living organisms walking the surface, it all makes up our environment. As it's defined here, the environment is the real world of interconnected living and non-living things surrounding the Earth. It's a delicate, highly balanced system. However, humanity has sort of become a geological force all on its own. Remember those non-renewable fossil fuels we discussed earlier? Yeah, our rapid burning of coal, oil, and natural gas to harvest energy is acting as a massive disruptive force. Human activities, alongside rapid urbanization, deforestation, and the heavy use of chemical fertilizers and pesticides, are driving some incredibly critical global issues. We're seeing accelerated global warming, harmful desertification, and the depletion of the ozone layer, which, by the way, is a highly reactive gas composed of 3 oxygen atoms that usually acts as our planet's protective shield. And all these human activities supercharge what is known as the greenhouse effect, because we're pumping vast amounts of gases straight into the atmosphere. A really prime example of this is methane. Methane is heavily released from the decaying of organic matter that we find in our waste dumps, animal dung, and massive expansive farmlands. So by fundamentally altering the very composition of our atmosphere, we're basically tweaking the climate controls that dictate our global weather. And that brings us to Section 5, the final question. Knowing how deeply connected the Earth's physical systems truly are, and knowing the fundamental difference between renewable and depletable energy, we kind of have to look inward. You are an active part of this environment. So the question is, how will your daily actions and your personal energy use impact the massive environmental forces shaping our world's future? It's definitely a heavy question, but an important one to chew on as you go about your day. Thanks for joining me on this explainer, and keep exploring the science that shapes our world.